Carbonated drinks, like soda, contain carbonic acid and carbon dioxide. When the soda can is closed, there is carbon dioxide at the top where no liquid is present. Soda cans also contain a high amount of pressure, which contributes to the bubbles produced. As you open the soda can, the pressure is released, allowing gas bubbles to rise to the surface. An unopened can does not have these bubbles because it still contains the pressure and carbon dioxide inside the bottle. Not only is there pressure released when you open the soda, but also the carbon dioxide that was initially at the top. This is what causes fizz to rise. This process when you open the soda can requires energy so the gas can break free from the liquid and overcome the force inside. This is why if you shake a soda can, you input energy which unleashes more tiny bubbles and explodes. If a soda can is left open or is placed in warm temperature, the carbon dioxide from the carbonic acid in the liquid slowly escapes, which decreases the fizz and amount of bubbles.
This is the process of adding the CO2 into the soda. It needs low temperatures and high pressure. It needs low temperature because the rate that the CO2 dissolves is affected by the temperature. The rate is increased as the temperature decreases. So at lower temperatures, it's easier and faster to put the CO2 into the soda. Normally, the temperature is lowered to about 36 to 41 degrees Fahrenheit. The soda also needs high pressure to get the CO2 into the mixture of like sugar, water, and any syrup or flavoring. This is done by putting the mixture into a pressurized tank, and CO2 is injected into the mixture. The amount of CO2 needed depends on the type of drink. Fruit drinks need less carbonization, while ginger ales and colas need more carbonization.
This is the pH scale, which determines the acidity of a beverage. As you can see, a pH of 0 to 6 is acidic, whereas 7 is neutral. So the closer a beverage's pH is to 7, the less acidic it is. For example, Coke is the most acidic soda with a pH of about 2.5, while root beer has the lowest level of acidity with a pH of 4.5. Most soft drinks contain one or more of these acids: citric acid, which is mostly fruity beverages, carbonic acid, and phosphoric acid. The chemical formulas are H2CO3, H3PO4, and C6H8O7. As you can see to the right, there is a picture with a list of sodas and their pH levels. Phosphoric acid is purposely added to soft drinks to give a sharper taste. Not only this, but it also helps slow the growth of bacteria, which normally would rapidly multiply. Almost all of the acidity in soda comes from the phosphoric acid, not the carbonic acid. You can see this by looking at the pH of fresh versus flat soda, because there's only a slight difference. Even though we love the taste of sodas, the question is, how does the acidity affect our health? One major effect is on our teeth. If we drink too much soda, especially for kids, the acidity and sugar can lead to tooth decay and other gum diseases. Not only this, but it can also lead to diabetes and a higher risk of heart disease.
When the top of the soda can is open, the pressure inside the bottle can decreases, causing the carbonization to escape, which is why it fizzes. So it's the CO2 kind of rising to the surface and then escaping because all of that pressure escaped. So it's not like holding it in. If it's left for long enough, the CO2 will leave, taking away the fizz and then that taste of the acid. So this is part of the reason why soda becomes flat. Another reason is heat. So the heat allows the gases to escape. This is the opposite of why you kept it cold when you were adding the CO2. It's just the reverse effect of that. So when you heat it up, instead of making it easier for CO2 to go into the mixture, it makes it easier for CO2 to leave. So ways to avoid a flat soda is don't shake the soda before you're drinking it. Don't leave it open for too long, and also keep it refrigerated.
The Mythbusters are going to have a blast. The most common theory about what's going on in this reaction between the candy and the soda is what's called nucleation. Basically, the idea is that the surface of the candy is covered with microscopic pits and lots of more surface area than you can actually see. And each little pit, each little corner provides what's called a nucleation site, or a place where a carbon dioxide bubble can form and escape. Look at a Mentos close up, and it's like the surface of the moon. And that might be the candy key. Drop one in cola, and every tiny crater provides a site where a CO2 molecule can change to gas. Because Mentos are so pitted, the theory is that millions of CO2 bubbles are formed in a very short space of time. And because the candy sinks and this rapid release of gas happens at the bottom of the cola, you get that famous fountain. To test this nucleation theory, they're going to start with a control. One regular mint Mentos dropped in soda water. And sure enough, it gets the bubbly party started. Now, to do a comparison.
These two candies are made by the same manufacturer, and as far as I'm aware, even using the same process. But the colored version of this actually has a glazing over it. It's a wax coating or a sealer that inhibits the nucleation process that the other one achieves quite readily.
The shiniest surface should lower the nucleation sites, meaning less of an immediate eruption.
That's not doing anything more than the wall of the plastic bottle itself.
Sure enough, with the smooth Mentos, there ain't no whiz with the fizz. The Mythbusters can say they finally cracked the case of the candy and cola cascade.
For the chem demonstration video, I'm going to shake up the can of Diet Coke, which has carbonization in it. And when I shake it, little bubbles in it are going to help quicken the release of carbon dioxide, so it's going to like explode because of the pressure. So yeah. Yep. This soda has been sitting in our refrigerator for a little bit, so that's probably why it did not explode as much as a freshly bought soda would have exploded, because when it sits, just naturally some of the carbonization is going to escape. Also for our video demonstration, I have a can of Diet Coke, and I'm going to see how long it takes for it to go flat. So I'm just going to open it. Oh, it's fizzing. I must have shaken it up before I grabbed it. But I'm going to pour it in this glass, and I'm just going to leave it out like unrefrigerated, and obviously unopened. And so right now, I mean, you can see by the fizz, but there are like the bubbles in it, the carbonization is still in it, and then after a few days I'll check back in and see what it looks like the difference. So yeah. This is after I just poured it in, but I'm just showing that there are still like bubbles in it, still carbonization. The carbon, not all of the carbon has escaped from the soda. This is 2 days for just sitting out, and as you can see kind of from here, it looks pretty flat. Don't really see any bubbles, even when I shake it up. I see no carbonization bubbles, so in 2 days of just sitting out, the soda's gone pretty flat. So yeah.